So this is a continuation of compound or composite transistors. Again, composite or compound transistors are circuits that have the same number of terminals as a transistor. So if you have a BJT-based composite transistor, it has a base, emitter, and collector. If you have a MOSFET-based composite transistor, you have a drain, gate, and source. There are mixed versions of compound transistors, but we won't be looking at those here. Okay. So the first one we looked at was the cascoded transistor, and let's take one of those. And move them down here. Our next one we're going to be looking at is what's called gain boosted. And the way a gain boosted composite transistor works is that, first of all, you have to start with a cascoded transistor. Actually, this one can go back over here. And on a gain boosted compound transistor, you have the same two transistors. They both have to be NMOS, or both have to be NPN, or they both have to be PNP, or they both have to be PMOS. But there is an addition to the circuit, and the circuit is another amplifier. And here's your collector now. Here's your base. And here's your emitter for this version. And again, this will be biased off some source, so it isn't counted as an input. Okay. The way and this works for BJTs also, but I'm just happen to be using MOSFETs in this example. The way this works is that this amplifier right here, let's look at just for the cascoded version. So this isn't the gain boosted version yet, but you get an R out equal to GM. Again, this is a MOSFET, so it's RO of the bottom transistor times RO of the top transistor. So this is M2, M1. And R out equals the GM of your top transistor times the RO of the two transistors. Again, you can find this by doing small signal analysis and approximating RO squared is much larger than either, as GM RO squared is much bigger than RO. And then the other terms drop out and you end up with this resistance. Okay, so the secret is when you add this amplifier right here, it actually increases the GM, the transconductance of M2. So you're still increasing R out, but you're doing that because the transconductance of this top transistor shows up in the R out equation. If you can increase this GM2, then you're increasing R out. Remember, the GM for this whole transistor is just the GM of M1. So your GM equals GM1. But what shows up in the R out equation is GM2. So just a second. All right. Okay. So let's look at gain boosted now. So this is for cascoded. For gain boosted, let's see what's going on here. What actually happens in this circuit is that this node moves a little bit, but it's harder to explain using that. So let's pretend that we have just a regular transistor. Do this and put V in here. And then let's look at the gain boosted version. And so this, these two, you can see I just took a transistor and put an amplifier on its input and took the inverting input and tied it to the emitter, the source. And that's exactly what I did here. Took the inverting input and just tied it to the source. The difference here is this is a bias voltage, so it's not moving. And in this actual circuit, this node's moving, which would move this node. But let's see what, let's look at it this way first, and then we can go back and make some adjustments to make it, to see what happens when it's the other input that moves. Okay, so if you look at this single transistor, if I move V in by delta V, I'll get some increase in I. And if you're in a legal small signal region, you can treat the change in I for a change in V as if it's linearly related. So part of using small signal analysis is assuming that your change in V in is over a small enough region such that all the changes in your circuit look like it's linearly related to it. And that's not really true. You know, with the VGS versus IDS, this is a curved graph. But if you take a small enough piece of it, it looks like a line. And so one of the requirements for the math for small signal analysis to work is that you're in a small enough region that you can say, hey, that kind of looks like a line. So in this example right here, what you'd have is delta V is proportional to delta I, since they're linearly related. So we can write it as delta V times some, let's do it this way actually. Let's do delta I is some constant times delta V, and it just so happens that that's GM. Okay, so delta I and delta V are related by the transconductance. Take how much the input moves, multiply by the transconductance, and that tells you how much your output current moves. Okay, then let's go over here. Let's see what happens. So again, I'm going to, I should show this as the change I'm looking at. I'm going to do the same thing. I'm going to add a delta V here. And the question is, give this a gain of AV. So if I change the non-inverting input by delta V, what happens at this node is actually however much delta V changed times AV. You're amplifying it and it's showing up at this node as delta V times AV. Okay, so now the change in voltage at the gate, if you are still in a legal small signal region, the change in voltage at the gate is proportional to the current coming out of your transistor, and it's multiplied by your GM. So what happens here is now your delta I is GM again, GM of this transistor times the change in voltage at the gate. But now the change in voltage at the gate is multiplied by the gain of this amplifier. Okay, and then just going one more step, what we're looking for is the transconductance of this amplifier. I just told you that the transconductance of the transistor is this GM. Let's solve for that. So in this case, you have GM equals delta I over delta V. Whereas over here, if you solve for GM, you get GM equals AV. Whoops. Delta V. Okay. Timeout. Okay, sorry, just a slight adjustment here. Instead of solving for GM right here, we know that your change in current here equals this. So if we're trying to find a GM for this entire circuit, we have the current, we have the change in current, which is GM delta V over delta V. So the current is GM delta V, and the change in the input is delta V. So if you put it over that, you can see that your GM is just the GM of your transistor. And then going over here, if you do the same thing, you have GM delta V AV. That is the change in current. So transconductance is the change in current over the change in voltage. And then you put it over the change in voltage. What you get is you get GM increased by a factor of AV. So if you put this amplifier in front of your transistor, it looks like if you draw a box around here. If you draw a box around here, now it looks like you have a transistor, a collector. You have a composite transistor with a drain, a source, and a gate, but now it looks like the transconductance is AV times bigger than it is with a just a single transistor. So this gain boosting increases the perceived GM, perceived transconductance of a transistor. And remember, we're starting with this circuit. And we know that the R out at that node equals GM2 equals GM2 times RO1, RO2. By putting this amplifier in front of this second transistor, then it looks like your second transistor, put the V bias on there, your second transistor has like the superpowered GM, which is now AV times the original GM of 2. So we'll put that as GM prime. Okay. And the gain boosting that happens here is because the voltage between the non-inverting and the inverting input move. And whether you move the inverting input or whether you move the non-inverting input, you're still changing the voltage between the two inputs, and you're still making this voltage change by AV. And if you're changing the voltage at this node by AV, that means that you're changing the current through your transistor by a factor of AV. And you end up with getting this increased GM transistor. It's perceived as a higher GM transistor. I know I went a little kind of a loop there, but I hope this made sense eventually. And you can only do gain boosting on cascoded transistors. So let's go one more step. I know this video is getting long, but let's do, we talked about where you can cascode both up and down to get a big gain. VB1, VB2, VB3. This is V out. For this, your gain would be AV, and this is a cascoded common emitter. So the active load has been cascoded and the bottom transistor has been cascoded. So you get a negative GM, we call this M1, 2, M3, M4, times, since these are MOSFETs, then you get a GM2, RO1, RO2 in parallel with GM3, RO3, RO4. That's the gain with just cascoding a common source amplifier. If you gain boost, then you're if you gain boost, try not to move this off the drawing screen, but if you gain boost, and let's say V in, I'm going to erase this in a second, so don't draw it if you're drawing, minus plus V bias, we'll make this 3. If we just do this, V bias 1, V bias 2, and have this as V out, what you get is AV, your GM is the same, GM1, like this M1, M2, M3, M4, and then looking down, you get it gain boosted, so you get AVRO, GM2, RO1, RO2 in parallel, and looking up, now you see GM3, RO3, RO4. But if you look at this, this is AV times bigger than this. This actually goes away, and you get approximately minus GM1, GM3, RO3, RO4. And that's because this resistance is 100 times bigger, or 1,000 times bigger, or 90 times bigger, whatever this AV is. So to actually get a really nice large gain, actually I won't erase this, just go down to the better version. See if I'm drawing over anything, I'm not. To get the better version, you actually have to gain boost both top and bottom. So you need to and now when you look at the gain of this whole thing, you have your regular GM1, that's your big GM. And then you have the resistance looking down, which we just did. That's AVGM2, RO1, RO2. But now looking up, you're getting the same, about the same resistance. Let's say both of these gain boosted amplifiers have the same gain. And you have GM3, RO3, RO4. And now you get massive gain. So if you figure that that's 100K, that's 100K, and that is, even if it's 1/100th, and figure that's like 100. Now these two cancel these out. you've got 10 to the 5th times 10 to the 5th. You've got 10 to the 10th divided by 2 if these are the same value. And if you put two resistors of the same value in parallel, it's divided by 2 times, let's say it's, this GM1 is 1/100th. Then you get 10 to the 8th over 2 as your gain of your amplifier, which is quite massive. Okay. There's actually more compound transistors. I'll do those in the next videos.